Alrighty. Okay, so I'm gonna get the class started. Okay, maybe it was a mistake to move here. Now, if we can just kind of jettison the second half of the classroom. Okay, I'm thinking about launching you guys to Mars, but we lack the technology right now, so. Okay, so we're gonna get started here. Are there any questions from the lab from last Wednesday? Because it is a lab that ends on this Wednesday, and it has been open the whole time, which means you guys could have been doing it the whole time, unless you're done already from last Wednesday. So any questions about that lab, which is the swap subroutine? You guys have to know how to access your parameters, how to dereference a parameter that is passed by pointer, which is tricky because when you use the registers, the first thing you get to is the address of the parameter itself. Okay, and then you dereference that, you get the parameter itself, which by itself is a pointer, but that's not what you want to access or change. It is what the pointer is pointing to. So you have to figure out how many dereferencing you need on both sides of the assignment operator, because the dereferencing happens once on the right-hand side to get the value that you need, and it happens on the left-hand side as well to specify which location you want to change. So that's something that you guys have to kind of figure out. I saw several programs that worked perfectly swapping the parameters, but not what the parameters are pointing to. So, and you can see that from the stack. Okay, so the stack is going to leave a trace of the effect of the program or the subroutine, and you can see from there, to see whether you're, missing one dereference basically. So, are there any questions about that homework assignment? No. No, you are turning in the source file, and you can turn it in as a text file. Text file would be good. Just text file is fine. Okay, so what we'll do today is to continue to talk about subroutines, but this time we'll be talking about how to nest a call of a subroutine to become a parameter in the call of possibly another subroutine. Can be the same subroutine, can be another subroutine. It doesn't really matter. Okay. So the best way to illustrate what we're going to do is to use an example. So I'm going to make an example right now in C, and we'll go ahead and talk about the concept first, and then we'll go ahead and implement the assembly code, and then we'll test the assembly code to make sure that it does work the way it's supposed to. Okay, so we'll use this particular mouse pad for that purpose, and I think we are good. I just need to move this window a little bit to the center. There we go. Okay, so for this one, we can just use int8_t, which means it is signed. Okay, it doesn't really matter in this case, because what we're doing is we're just using a subroutine to implement add. So the core part of the subroutine is easy. Okay, you give it two parameters. Okay, we'll just call it x and y. And what it returns is really just x plus y. Okay, so the subroutine itself, or the logic of the subroutine, is not the issue. There are no pointers here, no pointer type for the parameters. We are not doing any complicated stuff. There are no local variables. So in many ways, the subroutine itself is easier than the swap subroutine that you have to implement for your lab from last week. Okay, so the complicated part here has to do with the way we call it. So in other words, if I were to specify a main, okay, so int main, and then we specify some local variables. So we can specify int8_t, and you don't have to use int8_t. It's the same thing as char. We'll just have one local variable called, well, we'll call it n, just so that when we refer to the name, it is easy to identify. Are we talking about the main n local variable, or are we talking about x, y, which are parameters of the subroutine? And we're going to do something like this. Okay, n equals to, okay, we're going to call add. Except in the add parameters, we specify another add, and we can do, I don't know, 2, 20, and then we have another add of 4, 5. Okay. So first of all, do we have a problem in this code? Not counting, I forgot to include stdint.h, standard integer.h. But other than that, is there a problem with this code?
Is it possible to pass other function calls as parameters?
Well, if it returns the correct type, yes.
Okay.
So the idea of the return type of a subroutine, which in this case is basically a char or a signed 8-bit integer, is to specify where you can put the invocation of the subroutine. So since the parameter of add is basically the same thing, which is an 8-bit assigned integer, so if add itself is returning that type, it can certainly go where any other values of the same type can go. Okay? Yeah, go ahead. Did you have a question? No. No? Okay. So is that concept okay? All right. So if I were to compile this program, assuming I didn't make any stupid syntax mistakes, it would compile and it would run, and local variable n of main will end up with a value of 22 plus 9 is 31. Okay, so it should end up with a value of 31. So now the question is, how are we going to do this? In other words, are we nesting the invocations of add? In other words, at some time we're going to have 2 invocations of add at the same time, or what? Okay, so that becomes the next question. So the best way to illustrate what is going on when this code executes in a normal C program, not one of our TTPASM program that is equivalent to this, is to finish up this program, compile it, and then we use the debugger to figure out the execution path. Yep. I believe so, but it's always good to check. So it is on, and it is important to check the volume is fluctuating, because sometimes I forget to press the on button here, and this thing is really great, because if you have watched the video since I changed to this, you will notice my voice is always constant. Okay, it doesn't matter where I go, it's always the same. The bad thing is there's one more button to push, which I forget sometimes. So it's always good to check. Cool. All right, so this program is done. I am going to save it. The temp folder, we'll just call it add.c. Okay, I'm not feeling very creative today for these names. And we'll go get a bigger terminal. Come on, where's my big terminal? There we go. Go to the temp folder. GCC-G to include debug information. So if you want to use GDB to kind of track down the execution path of this program, -G is needed. And then you can just specify the name of the code. Or, okay, warn all is always good to have. It's going to spill out a little bit of warning because n has a value, but we never use it. So the compiler will tell us about it and go like, maybe something is wrong with it. But in reality, there's nothing wrong with it. So that's the only warning that I'm getting, which is good. So now we say gdb a.out. Unless you use the -o to specify the output file name, a.out is the default executable name in Linux. Okay, that's not working. That's not going to work in Windows, although Windows has been very Linux friendly lately. So maybe it does work in Windows. I don't know for sure. All right, so here's the program. I'm going to put a breakpoint on add. In other words, every single time we get into add, just getting into the beginning part of add, I'm going to stop. So I can look at the parameters to figure out, okay, what is it calling add with this time? What is it calling add with this time? And what is it going to call add with this time? Just looking at the program, let me finish listing the program. How many times do you think add is going to be called? Just all together. If you add up all the invocations, how many times? 3. Okay, that makes sense because you can see 3 add on line 11, which means it's going to call 3 times. But the question now is, are they going to stack up, okay? In the real sense of the word stack, okay? In other words, is one invocation going to be active and then another invocation of add is going to be active stacking on top of that? Or is it going to be 1, 1, 1? What do you think? It's going to be sequential 1, 1, 1. Very good. Okay, so we'll go ahead and run the program. And it stops the first time. And you can see right away, because when we are at a breakpoint, it automatically prints out which subroutine and what the parameters are like. So in this case, it's calling add with 4, 5 as parameters. Okay? Is that surprising? But that's the second parameter. Don't we read from left to right, and it should be calling 2 and 20 first? Hmm? Because of the stack. Okay, very good. Okay, I like where this is going. So why does the stack have anything to do with we are calling the second one first? That's the last parameter. Very good. Okay, so that's exactly what it is. Okay, because we push the last parameter first, and add 4, 5 turns out to be the value of the second argument. Okay, so it makes sense for the compiler to call this one first, so that it doesn't have to compute a value and then do a whole bunch of juggling just to make the stack look right. Doing this first, make sure the stack looks right without any extra work. Okay. I'm going to press continue here, C for continue, which means we're continuing the execution of this program at full speed, because there's no need to really stop and figure out what is in between. So this is the second call. The second call is 2 and 20. X is 2, Y is 20. Is that surprising you? Nope, because it's pushing the first parameter of the outermost call to add. Okay. If I continue one more time, what do you think you should see at breakpoint 1?
What is that
0 to 4 is a hexadecimal representation. When you see a number starting with starting with 0, that's the prefix of a octal or base 8 number in C. So 0 to 4 together is a base 8 number. Now, if it's base 8, it means it is 4 plus 2 times 8 plus 0 times 64. What is that? It's 20, known as 20 to us as a decimal number. So it really is specifying the same value as 20. The reason why it switches or gives us the alternative to look at this as a character in octal is because it is 8-bit wide. In other words, GDB is kind of a smartass. Okay, when it's an 8-bit signed something, it goes like, oh, it's a char. I know what a char is. I know what you want to display a char as too. So it'll try to display as a character. But 20 as 20 as an ASCII code or 2 as an ASCII code is not in the printable portion. It's not the ASCII code of a punctuation or a digit or a character in the alphabet. So that's why it only shows up as an octal number, because it's not printable. Okay, so that was a good question. I'm kind of surprised that you guys didn't learn about octal number in your C++ class. Sorry?
So they're only 16 weeks.
They're only 16 weeks, exactly. Which means we should make the semesters longer. Well, trust me, in some universities, they move a lot faster in classes. Okay, I'll give you one example since I mentioned that. When I was at San Francisco State University, which was not really well known for computer science nor engineering of any kind, okay? The C portion of our class, I was taking the operating system class. Now, do not confuse that operating system class with the operating system classes here, like cisp310 and the whole series. In that class, the operating system class is about the implementation of an operating system. It is not about the use of an operating system. So they were about it's about the coding behind an operating system. C, the introduction of the C programming language was kind of like the professor said, okay, does anyone know C programming here? Nobody knew because Pascal was the instructional programming language of the time. So nobody knew anything about C programming. So the professor said, well, in that case, you have 2 weeks to learn how to program in C, and starting on the 3rd week, we'll be starting to write the operating system in C. And that was it. And then later on, I moved to the University of Hong Kong and then retook the class of operating systems. Not because I flunked it the first time, but because in Hong Kong, everything is kind of rigid. It's the British system. So if you go in as a year 2 student, you are going to take these classes, which included operating system. And guess what? Same thing happened. So does anyone know anything about C programming? I see. Well, you got 2 weeks to learn it. And that was it. So as I said, there are universities that will actually push you to learn a new programming language a whole lot faster than we do it here. Just be mentally prepared. If you go to Berkeley, for instance, okay, they will throw whatever programming language that was applicable at the time and say, you got 1 week to learn it.
Sounds right.
Yep. Okay, so getting back to this one. What do you think the 3rd call of add is going to have as parameters? 22.9 is correct, okay? Because 22 is the first parameter, x equals 22 as a base 10 number, and then the second one is going to be 9. So that's exactly what's going to happen. So let's do a continue here, so we can hit add the 3rd time, and basically verify that x has a value of 22, y has a value of 9, and this is the 3rd call. So at all of this time, there's only one instance, there's only one invocation of add active at a time. There's no stacking up of add of any kind. So even though in syntax it looks like that's what's happening because we have 2 adds inside one big outer add, in terms of the invocation, it's all quote unquote flat, which means we call add the first time, we call add the second time, and then we call add the 3rd time. Is that okay? All right. So at this point, I'm going to stop in main. Okay, we'll just kind of put a breakpoint on line 12 so that when this is all done, we just double check to make sure that n has a value of 31 in decimal. Okay, because I really hate to know that n is not 31, and it does. It is 31, which by the way is also 7 times 1 plus 3 times 8. 3 times 8 is 24. 24 plus 7 is 31. Okay. So are there any questions about the tracing of this code in C? Why we have all those invocations of add the way that I showed in the demonstration? No questions? So good? All right, so now it's time to kind of convert that into assembly code. Okay, so this is a C code. I'm going to mess around with the C code, and instead I'm going to use another mouse pad, which it has hidden, to implement the assembly code. Okay, so we'll do this one thing at a time. Okay, here's main. I'm going to make it really simple because I want to finish the implementation of add first. So here's add, okay, which is a subroutine, a real subroutine unlike main. How are we going to do this? What is the one thing that we know at the entry point of add about what the stack pointer is pointing at and what is on top of what the stack pointer is pointing at? How much do we know about the stack at this time, right at the entry point of add? What do we know? The stack pointer is pointing at
The return address.
the return address. It is always pointing to the return address. Okay, very good. So I'm going to put some blanks here because I know some of you are copying by hand. So I'm not going to go back and insert lines because that makes it really difficult to copy. Okay, register D, which is our stack pointer, is pointing to the return address on stack. So I left some empty space here because what do you think the subroutine can count on, assuming the caller is playing by all the rules, is on top of what D is pointing at? And when I say on top, it is the address that is following what D is pointing at, a higher address. What is that?
X.
Parameter X. Very good. Okay, so that means Y is right here. So it is always important when you implement a subroutine to understand what the stack should look like when the subroutine is at the end at its entry point. Okay, so knowing all this stuff makes it kind of easy to deal with the rest. So there are many ways to do this. I typically like to make a copy of the stack pointer into some other register so I can do some calculations and move it around. And remember, you do not want to increment the stack pointer unless what the stack pointer is pointing at is no longer of use to you. Why is that the case? We talked about that too, but I just want to see if you guys remember. Interrupts, exactly. So in the case of a system that is not running in protected mode, or something that's running in protected mode and you're writing kernel code, anything that is below what the stack point is pointing at can change at any time without you knowing about it. Okay? Because the promise is, I'm not going to touch anything that the stack point is pointing at or above. That is safe. But anything that is below what the stack point is pointing at, the interrupt can use. So that means unless you're about ready to give up the return address, don't increment D. Because the moment you increment D, an interrupt can occur on a normal platform and therefore erasing or overwriting the return address. And there's no way the subroutine can even know about it. That's the biggest problem. Okay? So that's why if you need to calculate the address of something that is on above what the stack point is pointing at, make a copy of the stack pointer and then use the other register for calculation purposes. Okay, so I can now increment C. So if I want to make a comment here, I can now say that C is also pointing to the return address, or the other way to say it is register C is the address of the return address on stack. Once I increment it, C becomes the address of X. That's something that I need. Cool. I'm just going to use a load instruction. Put it into A. So register A is not the address of X. It is X. It is the value of the parameter. But we also need Y. Well, that's not too bad. Increment C one more time. Now C is the address of Y. And then we can put it into another register, say B. Okay, it doesn't matter which one. As long as it is not register D, it's okay. So now B is Y. And then we have the add instruction. It is important that we use this order because we want to store the result of the sum directly back into register A. Why? What is so special about register A? It's the return value. It's the register to pass the return value back to the caller. Okay? Now remember, all of these conventions are mirrors of actual conventions like this in GCC, in all basically well-known C compilers. Well, that depends on the architecture. But in the case of the Intel architecture, yes. Register A, EAX, or RAX. EAX is the 32-bit version, and then RAX is the 64-bit version. But the compiler, GCC, would use the same convention. It would choose to use register A for that purpose. Yep. And by the way, those letters in the Intel architecture is not arbitrary. It's not because ABCD turns out to be the first 4 letters of the alphabet. They're actually special purpose registers at one point. A used to stand for accumulator. B used to stand for base. C used to stand for counter. And then D used to stand for data, I think. So they were once special purpose registers, which means only certain instructions would implicitly use a particular register. But that was a long time ago. It's probably before the 8086 or 8088 days. So back in the 70s or even maybe earlier, they were special purpose registers. But the name stuck. So people just kind of kept using AX, BX, CX, DX, and so on. but at one point they were not, just general purpose registers. Okay, so getting back to here. So we got the return value calculated. The only thing left is to return back to where we came from. So we LDB again, this time with register D. All this time I didn't change D, so that means D is still pointing to the return address. Very good. Okay, so now B is the return address, not the address of that, it is the return address itself. Okay, once we have it in a register, we don't need that on the stack anymore. So increment D to deallocate the return address from the stack, and then the JMPB will return to the caller. So are we doing okay so far with this code? A lot of this is a reinforcement of things that we already have introduced in the past, but repetition makes it better. But this is not even the main focus of today's lecture, okay? Because the subroutine itself is relatively simple, 2 parameters. The main focus is from the caller's perspective. How are we going to do this? So first of all, we have to initialize the stack pointer. Technically speaking, that is not the job of main, so I'm going to move it out of main. Sub DD, okay, is to initialize the stack pointer. Also, technically, we don't have to do that, because when you reset the processor, every single register starts with a value of 0. But to emphasize that the stack needs to be initialized before you use the stack, we just put it here. There are certain cases where the stack still needs to be initialized, even though you may not be doing it manually. You will still have to kind of trigger the initialization of the stack using your own code. We are not going to kind of really get into that kind of programming in this class. If you start to use multi-threading in any type of C, C++ program, every thread has its own stack. But only the main thread or the initial thread has a stack that is pre-initialized by the operating system. All the other threads that this main thread starts, they do not have any pre-allocated stack. So the main thread has to, 1, allocate the stack, and then when it starts the thread, that particular call is going to initialize the stack pointer for that particular thread. Okay? So maybe you'll get into that in systems programming in Saxday. For those of you who are moving on to Saxday, they have a class called systems programming, which we used to teach at one point, but because of really, really low enrollment, we decided not to offer that class anymore. It's 453 in our catalog. If there's enough interest, we can restart that class. But over the past few times, we just couldn't fill that class, because it's mostly intended for people who are either transferring to Saxday or people who cannot take it from Saxday because they are not offering that. So we usually do not end up with enough students for that one. Okay, first thing first, we are decrementing D to allocate space for the local variable n. Okay, and when we do this, we're not going to put a value here. We just go like, okay, reserve a byte. Okay, it's not initialized. And then we can move on to this code here. So when you move on to this code from the GDB, we kind of know how to do the call, right? So remind me again, what is the parameters of the first call to add? 4, 5, very good, because it's the second parameter or the second argument of the outer add. We cannot do the outer add call unless we have both parameters already on the stack. So we can only call add 1 at a time. Okay, so we're going to call add with 5 and 4. All right, so we have LDI A with 5, okay, because 5 is technically the second parameter, which we should push first. Now this is add, so it's not really exactly order dependent, but I would like to preserve that as much as I can. Okay, so we decrement D again. This time we are allocating for parameter y of add. And then we do an st instruction to actually store the 5 on stack. Okay, so this is basically push 5, or the last step of pushing 5 on the stack. And then we have LDI A4, decrement D. This time we are allocating for parameter x, stda. So these 3 instructions is pushing the value of 4. Now we can call add the first time. So we do LDIA with return from add1, the first call to add. And I usually do this with an editor, but that makes it kind of difficult for you guys to copy. But since it's recording, it's not even recording, it's streaming. So unless there's another incident at YouTube, I don't think we're going to lose any video content. You guys knew about it, right? No? Okay, somebody else explain.
Well, she shot her boyfriend or husband. That's the one she was going after. So it was a little bit more to it than that.
So could have made it to Jerry Springer.
It could have.
Okay. Okay, very good. Since when you guys were explaining that, I finished the first part of the call. So we push 5, we push 4, we push the return address, and finally we continue execution at the subroutine. Okay. And when it comes back, we got some cleaning up to do. Okay, so I'm going to do the usual clean up code. Decrement D, this one is to deallocate the first parameter on the stack. Increment D again, we are deallocating the second parameter of stack, the second parameter from the stack. And now the stack is balanced again. But then we have to figure out what to do with the return value, because add is coming back with a return value. What is the purpose of add 4.5?
Parameter 2.
It's supposed to be parameter 2 of the outermost add call, right? Is that result, which is 9, on the stack right now? No, it's not on the stack right now. Nobody put it on the stack. Where is it now? In register A. Okay, so that means technically speaking, I need to allocate again on the stack. This time I'm allocating for the second argument of the third call of add. Okay, I'm using add3 to indicate that's the third call to add. Is that okay?
Well, we use return from add1. So
What? Say that one more time.
Earlier in line 10, we use return from line 1 or add1 when we push the third addition call. So are we because return from add1 or add3?
This is add1. That is correct, because that's the first call to add.
Okay.
So I'm counting the sequence of add as when it happens in time.
Okay,
not reading from left to right. Okay. So I'm naming the sequence.
Are you reading from right to left or left to right?
I'm not reading either, because the order of the add does not depend on how you read. It has to do with we push the second parameter first, or last parameter first. Okay. So the suffix of add has to do with, in this sequence of calling add, which one is it? Is it the first time we call add? Is it the second time we call add? Or is it the last time we call add? Okay? All right. So we have to allocate now for the second argument of add3, which is the last call to add. And then we have to store it on the stack. So std, which is A. Okay, so we are basically pushing add 4.5, or the result of add 4.5 on the stack. Is that okay? I mean, it's pushing 9 on the stack, but 9 is the result of adding 4 and 5. So are we okay with this? Yes?
That's the first of the parameters, and then go to the next one, yeah.
Yep. Okay, cool. So somebody is going to point out and say, oh, but then we can just delete line 16 and line 17 because I incremented and then I immediately decremented, right? And that is correct. I really do not need to increment first and then deallocate. And then decrement. But I really want to do it this way because the increment and the decrement are done to different constructs. The increment is to deallocate parameter y of add1. The decrement is to allocate for the second argument of add3. So functionally speaking, they serve completely different purposes, even though they still cancel out each other.
For the interrupt?
Huh?
Isn't it necessary for interrupt?
There's no interrupt here.
Oh, okay.
Interrupt is not going to have any effect on this. Okay? So are there any questions before we move on? Because the second half is kind of look exactly like this one.
This is a standard of, this is a programming standard. You have to do it just to keep the structure so that when you debug
Yes.
it, you know what you're looking for.
Yep.
Okay.
And your C program will do exactly the same way, but using the opcode of whatever commercial processor you're using at the time.
Right, yes.
Yeah, but the approach is the same. Yep. Is that okay? All right, cool. So now that we have pushed 4, 5 on the stack, what are we going to do next? Functionally speaking, from the C code, forget about assembly code. On the C code, what are we going to do next? Add 220 and we perform that operation, right? Okay, so we'll just go ahead and do that. So this is where it's going to be very tedious. Okay, so we have to load A with 20 decrement D std A. So all of this code is just to push 20 on the stack. LDI A with 2, decrement D again, std A. All this is just to push 2 on the stack. LDI A, return from add 2, return from add 2, define here. Decrement D, std A. All this stuff just to call the return address on the stack, but this time it's for the second call, okay? And that's why the label name is different. And then we just call the subroutine or continue execution in the subroutine with a jump I. So when we come back, we should do the same thing. We increment D to deallocate the 2 parameters or 2 arguments. You know, from this perspective, it's called the arguments. And then we decrement D again, because this time we have to allocate for the first argument of add3. Is that okay? In other words, we are done with add 220. The return value is stored in register A, but I don't want it to be in register A because the first argument is supposed to be on the stack just below the second argument. Okay? So I need to push it on the stack. So that's why I need to decrement D, std_a. So we are now pushing add 220 on the stack. Is that okay? So now, at this point, I have both arguments on the stack for add3. So there's nothing else. Well, okay, I shouldn't say nothing else. I do need to push one more thing. I need to push the return address of the third call to add. Okay, so LDIA again, return from add3 this time. Decrement D, store into D, or where D points to. And this time we are pushing another return address for add3. And then we continue execution and in add. Define return from add3 here. And then this time when I increment D, there's nothing to push time this time, right? Because I'm really done, completely done with the right-hand side of the assignment operator. But the assignment operator itself is not done because I only got the right-hand side done. I still have to copy that value into whatever the left-hand side is specifying. The left-hand side specifies the local variable n. Who's pointing at n? Do we have anything pointing at n right now? Is the stack balanced? The stack is balanced, which means the stack pointer is pointing to the same thing before line 11 even happened. So where do you think the stack pointer should be pointing at right before line 11 even started?
Address of n.
Not, well, okay, D does not point to the address of n. D is the address of n. So at this point, D is the address of n. Because the stack is once again balanced, okay, it has basically gone back to the same state as what it was before line 11 started. So D is pointing at local variable n, which is very handy for us because the next operation is just a st instruction to whatever D points to, whatever A has, which is the return value of the third call to add. We store it into n at this point. So now we're done with line 11. And of course, this looks kind of silly because now we have to deallocate the local variable itself because we are treating n just like we're treating main just like any other subroutine until we get to the point where we have to return. Then we just go like, no, this is main. It's a little bit special in assembly. We just halt instead of return. Okay. So after this point, then we just put a halt here because we are done with main at this point. All right. So are there any questions about all this stuff here? No questions? I know it is tedious, okay? So not counting the tedious part is the concept okay. We push 5, we push 4, we push the return address, we call add. We return, we pop the 2 arguments, but then we push the return value. And then we push 20, we push 2, we call add again. When add returns, I pop the 2 arguments because they are not useful anymore. They should not be using the stack space. And then I push the return value of add 220. At this point, we have 2 arguments on the stack. We have the argument which is 9, add 4, 5. We have the other argument which is 22, which is because of the result of adding 2 to 20. Those 2 things are now on the stack. So now we push the return address of the third call to add on the stack. We call add one last time, which is the third time. It comes back. We deallocate these 2 arguments from the stack because they are not needed anymore. But the return value is in A. But because the stack should be balanced compared to what it was before all of these calls, D should be pointing back to whatever it was allocated to in the first place. So D is now pointing to n again. So we just have to store whatever A has at register A to whatever D is pointing to, and that accomplishes line 11. Is that okay? Concept-wise. Yep.
So I had a quick question. So after you hit the add, and
Which add? Because we got 3.
right before the 2 and 20. So if
Uh-huh.
you did pop after that, would the 2 and the 20 be on the stack with the other value, the other add one that we did? So would those values still be on the stack if you hadn't popped them?
That is correct.
Okay. So if you do
Because the callee, the subroutine being called, is only responsible to pop the return address. The arguments were pushed by the caller. So the caller is the only one to deallocate the arguments. Now you might ask, but why is the subroutine not responsible to deallocate the arguments?
Because they have to deallocate the local variables.
Well, the subroutine has to deallocate its own local variables for sure, because nobody else can even know how much space is used for local variables. But what about the arguments? Because don't you think the subroutine is supposed to know the number of arguments as well? Now remember, we are talking about C and C++ here, and not just any other programming languages. Pretty sure I have introduced this concept before. In C, you can actually write a subroutine like this. The ... is representing a variable number of arguments, which means the subroutine actually does not know, not necessarily, how many arguments is actually pushed on the stack. Okay? It can guarantee 1, right? But there's no telling how many more arguments is actually on the stack. The caller has to know. Because after all, the caller is the one responsible to push all the arguments on the stack. So this is the reason why the caller is responsible to deallocate the stack space used by the arguments, not the subroutine being called. But the return address has to be there. And because of the implementation of the instruction return is usually its own instruction, the subroutine is responsible to do that. I'm explaining this because once we understand the rationale, it becomes, well, okay, to me, it becomes easier to understand and remember which one is which one. Okay, arguments is the caller's responsibility to deallocate. The return address is the responsibility of the called subroutine to deallocate. So are we still doing okay with this stuff? Okay.
Argument is the actual value, and parameter is the variable, or?
Yeah, so that's kind of like a terminology thing.
Yeah, no.
So from the perspective of the caller, 4 and 5 are called the arguments. From the perspective of the called subroutine, x, y are the parameters.
Okay, arguments are sent, parameters are dealt with.
Yeah, arguments is seen from the perspective of the caller, and then parameters are seen from the perspective of the callee.
Okay.
Or at least that's my understanding. Let me double check.
I'll wait to write.
I don't mind being wrong, but I need to know the truth.
The truth is out there.
Can I handle the truth? Well, it is kind of important because understanding the correct terminology means that in future classes you understand what the other professor is saying, right? Okay, so it says right here a parameter is a variable in a method definition, method being a subroutine in an object-oriented way. When a method is called, the arguments are the data you pass into the method's parameters. Parameter is a variable in the declaration of a function. Argument is the actual value of this variable that gets passed to the function. But only the caller knows what it is. The callee obviously cannot know what value is actually being passed to the parameter. Is that okay? Mm-hmm. So I think my explanation is consistent with this, even though it's not the same.
It sounds like the same.
Okay. Close enough. So are we still doing okay so far with all this code? Yes. Okay. All right. So getting back to the assembly code implementation, I could claim this code is the same. I can say all kinds of yada, yada, yada. But at the end of the day, how do we know this code actually is correct? That it works the way it's supposed to?
Logism.
Logism, exactly. So we're going to run it to the Logism. Okay, so copy. And go to the share folder, processor, assembler. Okay. And then we just paste it here. Uh-oh, that's, okay, it is correct, okay. I just got thrown off by the first subtract dd instruction here. And then we move on to, I protected all of the other tabs, by the way, so if you want to make a new copy of the assembler file, it makes it much harder to kind of paste your code at the wrong place, yes. It happens.
That's why I keep going back to your original file.
Okay, so we just call this add.csv, put it into the temp folder, and then we'll go ahead and start up the Logisim Java. Ooh, all this time I didn't plug in my power plug correctly. Now it's starting to charge.
Oh, you're over halfway.
Yeah, it's only at 67%, so it's actually not too bad. It's not consuming energy like there's no tomorrow. Okay, so we'll go ahead and load the program first. I called it add.csv. Here we go. Okay, So to test this code, we can just run the whole thing and then look at the stack and see whether we have the remnant of n on the stack, right? Now that is only workable because we don't have interrupts. If we had interrupts, it is possible that you won't see anything like that on the stack because the interrupt can happen right after the end of the entire program and therefore overwriting everything that we are leaving behind. Okay, so that means that's not a reliable way to do it, even though for the toy processor it's okay because we don't really have interrupts. But I want to show you guys how to do it even if there are interrupts happening. Okay, so you go to simulate, you go to logging, and we do the usual thing. We keep track of the program counter. Change it to base 16. We'll go ahead and track down the stack pointer, which is register D, and change it to base 16. I'll just go ahead and track down some of the RAM locations, not all, because we don't really need all of those RAM locations. So how many locations do you think I should track? In other words, without running the program first with D being traced, do you think we can just kind of calculate how many locations on the stack we're going to consume at the maximum? So let's go back to the program and we'll do some counting. And we just need to look at the C code too, because I think at this point we can look at the C code and just do the counting. 1 byte is n, right? Okay, 2, 3. Okay, for those 2 arguments, but we deallocate those 2. So we got back only one thing on the stack. And then we push it on the stack, 2. Okay, 3, 4, but we pop these 2, so we got 2 again, right? And then we push the result of adding 2 to 20 on the stack, 3 bytes. Oh, I forgot all the return address, by the way. Okay, but after we push add 4, 5, add to 20, then we have the return address. So we're using 4 bytes on the stack. And then after that, we're just unwinding stuff. So we're only using 4 bytes on the stack. So if I track the last 5 locations, I should see that the 5th location, or the lowest of the 5 locations, do not get changed. Okay, so it's always good to track a little bit more than what you think is going to be used, just in case. Okay. So now we switch back to LogicSim, and then we go to RAM, and then we just go to the last 5 locations, which is going to be 251, 252, 255, and 254, and then 255. So the last 5 locations, 251, 252, 253, 254, 255. And we'll change these to hexadecimal so that they don't take up too much space. And okay, there we go. And we'll log everything to a file. I just like to log it in the file just so that, in case LogicSim crashes, hey, we have a file, and the file can be imported into a spreadsheet, which makes it very handy for, just doing any type of post-processing. There we go. Close the window. We got everything all set up. Control K to start clocking. And it's all done. Okay. Now we just need to import the TSV file back into a Google Sheet document. You don't have to use Google Sheets. You can use Excel if you want to. But since I have Google Sheet here already, might as well. So we're going to open a new spreadsheet and import from the TSV, or tab separated value file. So import, and we're going to do some upload. And it is add.tsv. The only thing we need to change is do not convert text to numbers. Everything else will work just fine. And here's the content. All right. We can always change these locations just a little bit because it's pretty hard to read the way it is. So I changed this to register D. I changed this to RAM location 251, RAM location 252, 253, 254, and the last one, 255. Now remember the stack is initially here. We're growing the stack backwards, okay? Now if you're like my son, reading his novels, this is how he reads. He goes to the end, he goes like, we got 31 in the register. It's cool. Mom, we can return the book. So, if we don't have time to return the book, he might actually go back to the earlier parts and read some other chapters, but in completely random orders. It's amazing watching him how he reads a book. And we're talking about storybook. We're not talking about a reference book, which I would read in random order as well, as needed, right? But he's reading a book, like a storybook. He would read the first page, last page, and then go like, I guess, and then read somewhere in between in some random order. Okay, but we do have the right result, okay? This is when the program ends, okay? So when the program ends, this is the program counter, this is the stack pointer. The stack pointer is balanced. In other words, it went all the way back to 0, 0, which is a good sign. This is our register, this is our local variable n. It ends up with a hexadecimal value of 1f. 1f is 15 plus 16, which turns out to be 31. Okay, so that seems right. 9 is 9, okay, which is our second argument, which is the add 4, 5. 16 is 16 plus 6, because this 16 is in base 16, so the 1 is actually 16 in terms of value. So that's 22. Okay, that seems to be okay too. This is 2C, which is the return address of all that stuff. So we look up 2C and check that out. Okay, I can see a problem here already, which is something that I did not predict. So we'll look for an explanation after this. So we want to look at location 2C, or the definition of return from add3, and kind of so that we can confirm, oops, too much. Okay, do it slower. There we go. Okay, so we are looking at this particular location. Is it at 2C? 44 is the base 10 version. 2C is the base 16 version. So it is, in fact, the return address. But I saw one little problem. Okay, I'm not sure how many you've picked it up. What is this 22 doing here? Or 22 in hexadecimal doing here? It's a return address. It looks like a return address to me. So why do we have this return address on the stack? Okay, so let's count it again. This is n. This served multiple purpose. Initially, it served the purpose of, is it 5 first? Yeah, 5 for return address. Pop, pop, pop. Push the 9 here. Okay? This location also served multiple purpose. It was 20 to the return address of add2. Pop, pop, pop. Push 22 on the stack. Push the return address of add3. That's why this location is 22 in hexadecimal, because it was storing the return address of the second call to add. Is that okay? Well, just because I claim that doesn't mean that is the case. How do you know? How do you look at this trace and figure out, oh, did we really use this location as the return address of add2? There are two ways to do it, okay? And we should do it in both directions. The first one is to go back to the assembler, okay? And then we look at the definition of return from add2 and go like, oh, okay, that label really is 22 in hexadecimal. But just because it is 22 in hexadecimal can be a coincidence. we could be storing something else that turns out to have the same value as the return address. That's entirely possible. Okay. So what else do we need to look at in the trace or in the log this time to say that, oh yeah, this is the return address. We used it as a return address. Who put it there? We want to figure out which instruction put 22 on the stack at this location. Because once we figure out which instruction is responsible to do it, we go back to the assembler and then we check whether that instruction is a part of the pushing of the return address of add2.
So we got to scroll up and find the guy.
We scroll up until it is until we find the transition from 0, 0 to 2, 2. Okay, so here we see the transition right there. So the transition happens when the program counter is 2, 0. Now I didn't say the address of the instruction is 2, 0. I said the program counter is 2, 0. Because by the time you see the effect of an instruction, the program counter has moved on already. Okay, so the address of the instruction corresponding to whatever instruction that is actually putting 2, 2 on the stack is at location 1F. Is that making any sense? So now we go back to the assembler. We go to location 1F, and then we ask, is that the push instruction to push the return address? We look at this instruction here, and we say, okay, are you the one actually pushing the return address on the stack? All the comments are gone in this tab, but we can go back to the other one. So we can go back to the source tab. So, oops, click the wrong button. Undo.
Scroll.
Yeah, I was intending to scroll here. So we go back to source, and it's on about row 27, which is not exact. Oh, it is row 27. Cool. Okay, so it's row 27, and guess what? We did in fact push the return address with that instruction. So did you guys see how I'm really not trusting myself? Because I really need to know if my prediction is off, because I said, okay, it's going to use only 4 locations, but it ended up using 5, right? So I had a pretty good hunch of, oh yeah, I missed that. But I need to double check. But how did I double check? This. This is also how you debug a program. Because when your program doesn't work the way it is supposed to, it is deviating from your expectation, then it's a matter of trying to explain that deviation. So until you can explain that deviation, you really should not stop.
You gotta find the gremlin.
Yep, exactly. We got 15 minutes left, so I'm going to show you some bugs that you may have encountered and you will encounter that are really difficult to explain unless you know what is happening on the stack. Is that okay? All right. Because all of this relates to not really assembly language programming, but more so it is related to how C programs work in general. I'm guessing most of you are not going to program in assembly once you are not in a class that is in programming in assembly. But most of you will still end up programming in C, C++, or some other stack-based programming language. So that's why it is important to know this stuff. Okay, so I'm going to go here, and then we'll mess around a little bit here. Okay, so I'm going to go make a program called bad stack. Okay. Okay, and we have a function call here. It is function f. Function f doesn't do a whole lot, okay, except it has an array inside. So we'll say that pound include stdint.h so that I can refer to the size of integers. So we have a uint64 underscore t. This is an array of, say, 2 elements. Okay, it doesn't really matter what it is. And I'm going to say a bracket 6 plus equal to, okay, let's make it minus equal to something. I'm guessing that's going to be 8 plus 1, which is 9 bytes. Okay, I'm just guessing, which may or may not be the case. This one is I have to use some trial and error to actually get it to work, but eventually we'll figure this out. So we call f here, return 0. Okay. Do you guys want it to be? Okay, I think this one, if I can get this one to fail the way it does, it is already unexplainable using what you already know in C and C++ without using what you learned from this class. Okay. You look at void, f, you go like, that's not right. The array only has 2 elements. I'm trying to access the 7th element because we count from 0, right? So now the question is, something is going to get a value of 9, or something is going to be subtracted by 9. But the question is, what is going to be subtracted by 9? Who knows, right? Or do we have a guess? Because it's going to look at something that would otherwise be known as the 7th element of A. It's going to grab that 64-bit thing and go like, you're now 9 less than before. Okay? So now the question is, who's going to get that treatment? It's not one of the 2 actual elements in array A. Yep.
That was just going to be my guess. It was going to be the number 2.
Okay. So the way we're going to do this is we're going to use the debugger. Okay. In order for me to control the crash behavior or the wrong behavior of this program, I'm going to use the debugger to kind of help me a little bit, because the 64-bit architecture allocates the stack a little bit differently from the 32-bit, which is what I'm really familiar with. So I'm going to do a gcc-g bad stack. Okay. gdb a.out. Put a breakpoint in, is it function F or G?
F.
F, okay. So we then run the program. Okay, cool. All right, so we are now in this particular subroutine. The first thing I'm going to do is to know the approximate range of the program counter at this point. Okay, there are several ways to do it. I can say print main. Okay, print main is going to print main as an address. So main has an address of, well, that looks kind of coincidental. Okay, I'm not trusting that. I'm pretty sure that is the case, but it just looks kind of funky. Yep, okay. So the entire program is residing at a location that has a whole bunch of 5s and then 4660, 4673-ish, okay? I just need to know the approximate range. That's all I need. So at this point, which is now in F, right, I'm going to print the array A. But I'm not going to print the whole thing out. I'm going to print with a /x because I want to print in hexadecimal. I'm going to print it like 1 by 1. The one I'm going to print is not A bracket 0 or A bracket 1 because they're actual elements in the array. They're uninitialized. They're of no interest to me whatsoever. I'm going to start with 2, which is the 3rd element of the stack, of the array. Is that okay? Okay, that looks like something on the stack. Okay, so maybe it's the frame pointer. Aha! I found what I need. What does that look like to you? If you look at $1, it is the address of the main subroutine. If you look at $2, it is the address of F itself. And then we see something like here, where do you think it belongs to? Which subroutine owns this particular address? Main owns it, okay? It's on the stack. How do we know this is on the stack? Which is one key concept at this point. No. The reason why we know it's on the stack is because array A is on the stack. Every local variable is on the stack unless you specifically say it is static. Is that okay? So A, which is an array, behaves just like any other variable that you define on as a local variable. It is on the stack. So A bracket 0 is on the stack. A bracket 2 is on the, A bracket 0 is on the stack. A bracket 1 is on the stack. So A bracket 2, even though we did not allocate for it, it's on the stack. It is corresponding to the address of something else on the stack. Same thing with A bracket 3. It is corresponding to something else on the stack. We did not allocate for it. Array A does not actually have an element 3. but we can go through A bracket 3 to access it. And it looks like the address of code that we can execute. What do you think is on the stack that looks like the address of some code? The return address of something. The return address of something looks like this with a 64-bit architecture. Okay, so now I know what to mess around with. Okay, so I'm going to mess around with this one. Now, just to make sure that the program, okay, so we'll quit this program, and we go back to the source code, because now I know which one I need to kind of mess around. Okay, and I specifically chose 9 to decrement, because the address itself is taking up 8 bytes. The call opcode is taking up that 1 extra byte. I'm rolling back the return address by 9 locations. And what do you think the program is going to do?
Get lost.
It won't get lost. It's worse than that. Huh? Nope. It's not. Well, okay, that location is overwritten, but as a result of overwriting that, what do you think the program itself is going to do? It will behave as if it is in the loop, because it is returning to an address that is 9 locations or 9 bytes before the intended landing location. And guess what is 9 locations before the landing location? The call itself. So you call, it returns, but when it returns, it's not returning to the byte that is after the call instruction. It's returning right into the call instruction that got us into the subroutine to begin with. So it would just be infinitely calling the subroutine without proceeding any further after this point. Okay? We got 5 minutes. We can test it. All right, so gcc-g bat stack. Okay, there we go. gdb out. Put a breakpoint into the subroutine, which is F. Okay, run the program. This is the first call. Continue. And we have a segmentation fault, which means I misunderstood the length of that instruction. Okay. That's okay. Okay, I got a way to fix this or mess around with this. We run the program one more time. Okay, now we're into here. So what we're going to do is we'll print /x again, A bracket 3, which already kind of know what it is. So in order to figure out where the call instruction is, because I'm not familiar with the binary version of the call instruction in the Intel 64-bit mode, or otherwise known as AMD 64 instruction set, I'm going to do the X command, which is examine. Of course, I haven't used it for a while, so I'm going to use help to figure out what I need to look at. What I'm looking at is disassembling, which is I. So x/I, which means examine and interpret what it is seeing as instructions. And then now we have to tell it where I need to disassemble. So we'll just go ahead and copy and paste this. But we want to roll it back a little bit. So we'll say F1, 8.1. So roll back maybe 6, 7, no, take it 9 bytes or so. So 88, 80. Okay, so let's try 80 first. Okay, that doesn't work. That's okay. That took up some number of bytes. 2, no, 3, 4. Do you see what I'm doing? I'm trying to figure out where the call instruction is located. 8, 9, A, whoops, B, C. No, that doesn't look like it. D, E. Nope, none of this looks like the call instruction. Okay. So this is disassembling the whole program from main. And we can now see that the call, which is call queue, is at location 7C. We know the location is 8.1, right? So they're off by 5. So if I subtract 5, it would have gone back to the call queue instruction, and it would call again. It would return, but when it returns, because I messed up the return address intentionally, it will instead of returning to the move instruction, which is at location 4681, it will return back to 467C. So we got 2 minutes because we're in this room already. There's no need for you guys to move, so I got extra time to talk. Okay, so now we can doctor this program one more time. I was overestimating because the call actually only used 5 bytes instead of 9 bytes. So we'll go ahead and GCC this again, and gdb a.out, put a breakpoint in function f, run the program again, continue, 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 and it will keep staying in this loop forever. So next time when you have a C program, or even C++, that does something like this, the subroutine you're calling has no loop whatsoever. The code that is calling it has no loop whatsoever, but it behaves as if it is in a loop. Guess what? You messed up the stack. That's one messy thing you can do. Now, there are other even messier things you can do. Okay? This one is kind of obvious. Okay? Your subroutine, your program just doesn't go forward anymore. It is also possible for callee to mess up the local variable of the caller, because you just have to push it further. Okay? You will get to the local variable of the caller eventually, because the local variable of the caller is sitting higher up on the stack. The local variable of the callee is sitting lower on the stack. So if one of your local variable is an array, and you're indexing it out of range, depending on how far out of range, you can be touching local variables of the caller. So the subroutine is not going to crash. The caller is not going to crash. But the local variables of the caller is now not the same as before. The worst thing is not just to assign a new value like 0 into it. The worst thing is what I just did. You're adding some small amount or subtracting some small amount, so it becomes much more difficult to spot who messed this up. You're telling me that you have never gotten into problems like this.
Oh, I've definitely done that before. I was like, who messed it up right now? Yeah, I've definitely had a program where it's like, I run it and it's stuck in a loop. I'm like, I don't understand. It shouldn't be looping. But yeah, it was some miscalled variable.
Yep. Now, if you want something even more fun, I'll show you something even more fun. Okay, this is even better. Okay, so we got G here. Okay, so I would need like 1 or 2 try to get this one to work. Okay, so my objective is when F returns, it is not returning back to main, it is returning to G, which was never called anywhere in this entire program. Is that okay? No, it's not okay, but that's the whole point. Okay, so GCC, GDB, put a breakpoint in F. Okay, so run the program, print a bracket 3. Okay, /x. That's why hexadecimal numbers are better, because it's just easier to read when they're huge. Okay, so this time I'm also going to print /xg. Okay, I want to find out where G is. Did I call it G? Okay, there we go. So now I'm just looking at these numbers and go like 8860. They're off by 28 in hexadecimal, which is 8 plus 32, which is 40. Okay. So we just need to subtract 40 this time. So we look at the code again, and we say subtract 40, which looks kind of innocent, right? Well, we're just subtracting 40 from some array element. GCC, GDB, put a breakpoint in F, and then we'll just run the program. It will get to F just fine. That's not a problem. Single step, we are now at the end of function F. If I single step, it will quote unquote return into G. We know it's in G because it is It says it's in G, and we are on line 3. But out of this entire program, there was not a single call to G. G is only here for decoration, but somehow we got there. Have you guys encountered this problem before?
Usually it's like when I'm trying to add 1 or minus 1 to the end of whatever I'm looping through, and I'll get stuck at the wrong one. Either I'll go over or I won't go far enough. And
Yeah.
something like that's what happens.
Yeah, but if you just use what you learned in cisp310, I don't even care whether you ace that class or not. Even if you ace that class, there's not enough concept in cisp310 that can explain this. But once you understand the underlying use of the stack, like every local variable is on the stack, and the later the call, the lower the location, then you start to understand, go like, oh, all kinds of really bad things can happen. Okay? Some of this can cause what we call stack overflow exploits. Now, stack overflow exploits cannot happen anymore because processors now have a execution inhibit bit that can basically say you cannot execute any code that is in the stack space. Okay? So that stops certain kinds of exploits, but not every single kind of exploits. Because if you can still change the return address, you can still make your program, or not your program, somebody else's program, to return to the wrong place and therefore accomplish something that you, or the hacker, wants the program to accomplish. Does that make any sense? But you can see how I can just kind of manipulate that one single statement so that the program just go like, whoop, going here, whoop, going there. And the worst part is it's not crashing. It's just going to the wrong place, which is worse than crashing. Because crashing means, okay, we got a segmentation fault, got to fix it. This is not crashing, especially the first one, getting into quote unquote the loop. It's not crashing at all. But if you just look at the source code, there's no way to explain it. So next time when you write a C or C++ program and there's some really wacky behavior that you cannot explain using only C and C++ concepts, you might be overwriting somewhere on the stack. And the most likely way that you're overwriting something on the stack is array indexing out of bound, or you're using pointer arithmetics. You're incrementing a pointer, that used to point to something that you own. You keep going, and at some point, it's not pointing to what you own anymore. It's pointing to what somebody else owns at that point. So those are the tricky things that can happen when you use C and C++. Java has no problem like this. Why do you think Java has no such problems? This is unique to C and C++. Visual Basic doesn't have a problem like this. Why do you think that is the case?
Obviously the stack, I guess.
Oh, they use the stack just fine. It's not because they don't use the stack. It's because every time you do array indexing, they check the boundaries. C and C++ does not care. Okay? To C and C++, all you're doing here with the A and the square bracket is, assume this location is the beginning of array A. But the compiler never checks about, array A only has 2 elements. You're trying to access the 4th element. That should not happen. Okay? It doesn't check. Visual Basic does. Java does. So they will give you a runtime error right away on this line and it will say index bound out of bound or something along that line. It will just stop right there. C just fails silently, and it messes up something else. So when the symptom does show up, it's really hard to track back to this line. Some of you go like this, oh yeah, we can see clearly that this is the line that's responsible. Well, if your code has thousands of lines, okay, and you're using auto increment of some kind of index in some kind of a loop that is inside a conditional statement, it becomes impossible to find. Yep. If you're using the class or the template class, maybe. Because in that case, you're overloading the indexing operator, so you can put in your own bound checking thing. This is using just a plain C array or C++ array construct, which has no boundary checking whatsoever.
Array, not a vector.
Yeah. Or
I think I wrote a program that was like 200 lines long, and something like that happened. I just scrapped it and started over. I
now,
wasn't
if
having any hope.
now if this doesn't work for you, you can always do something like this. It means exactly the same, but using different syntax. Because in this case, A is used as a pointer, as an address. When you add something to an address, you are basically saying, okay, skip 3 things, right, in this case. But that would still be an address. When you dereference that address, it becomes the same thing as array indexing. But this means that if you assign the address of the array to a pointer and increment it 3 times, you end up at the same location. And that becomes almost impossible to spot, because all you can see is a pointer getting auto-incremented and then dereferencing. And it's not even clear how many spots it is over. So all kinds of problems like this can happen in C because there's no bound checking when we do array indexing. And 2, we can do pointer arithmetic and dereference any pointer and just say, store something over there. And not only that, you can say, yeah, this pointer says it is an integer over there, but guess what? I want you to pretend that it is a structure. Typecast the pointer into something else, into a pointer to something else, dereference it. Now we can do all kinds of corruption.
Oh, wow.
Yes.
You just write over everything.
Hmm?
So you just write over everything with that.
Oh, you can do massive damage to your own program. There's a book called Leave Robe Long Enough to Shoot Yourself in the Foot in C language. I think that should find it. Okay, programming language. There's a book in Amazon. Okay. There we go. There's actually a book that is titled Enough Rope to Shoot Yourself in the Foot 16 times over. I added that part, but it's actually more than 16 ways to do it.
That might be worth buying.
Well, the rating is not that good, but somebody actually spent the time to write a book with this title. It has to be indicative of something. So the main purpose of this class is not really to teach you guys how to program in TTP-ASM. Okay? Other than this class, I do not know of any application of the toy processor that we use in this class. In other words, from that perspective, you just wasted a whole semester. On the other hand, once you understand how C construct both control structure, subroutines, local variables, pointers, and all of that stuff maps to assembly code, and how things are stored on the stack dynamically when you run your program, that might help you debug a program that otherwise would be impossible to diagnose. That is the actual value, the true value of this class. Trademarked. Is that okay? Because I do want you guys to walk away from this class knowing that you have learned something that's useful. Unlike your other classes. Now, every single class has something that is useful. But in this class, I know exactly why it is useful. Because guess what? I have been bitten by those symptoms that I was just talking about. But at the time, I did not understand enough about how the stack was used. But thinking back, then I go like, oh, so that's what happened. All right. Well, the lecture's over. You guys can stay here and continue to work on the program that we started last Wednesday. Okay, if you have questions to ask, I can answer those. Or if you want to go back home and get dinner, okay, I'm not going to stop you.
But do you want to work on it? Maybe we can do it again. So I won't use my answers.
I'm going to stop the recorder.